So the idea is, and the reason that we teach limits, is that special form of limits were used to develop the derivative rules for calculus. And in fact, in most calculus courses, derivatives are taught first so that you see where the rules come from. There are a lot of things about limits that make more sense if we do them after we know how to take derivatives, though, which is why I reverse the order. So what was happening when the derivative rules were developed was that mathematicians were thinking of the derivative as the slope of the tangent line at a particular point. And so they tried to determine the slope of this line by finding the limit of the slopes of lines getting closer and closer and closer to it. Because you see, if we only have one dot, we can't find the rise over run just at that dot because we can't go up or over. However, run just at that dot because we can't go up or over. However, if we start further away, let's say over down here, then we have two dots. And we can draw a line, and we can find the slope of that from here to here. But the problem is, you can see that this green line here, the slope is positive, but it's not really very similar to the slope of this pink line right here. And so what they did was they said, okay, well, let's get a little bit closer. So let's go like right here. And then they said, alrighty, let's find the slope of this line. And the slope of this blue line isn't exactly on. It's not exactly right. Here, I'll zoom in so you can see that a little bit better. It's not exactly the slope of this green line, but it is a little bit closer. And if they just kept moving this dot and moving this line closer and closer and closer and closer, the limit of this process is getting it so infinitely close to that dot that we can see what the slope wants to be at this pink line right here. That was the idea of what they were working with. And so one thing that they could do is they could just calculate the value of each slope and just sort of do a table and figure out what the derivative was going to be that way. But mathematicians represent this algebraically instead because they're mathematicians. That's kind of what we do. These are called secant lines when they're between two dots. I should say, and variables. So, if we zoom in on this picture that we had above, let's say we have our secant line right here. So what mathematicians did is they said, you know what? We're just going to let that be x, some number, any number. We really don't care. And from x, we're just going to go up and over in order to get to our next point. So like up and over like that. And we're going to let the distance that we go over be h. So what that means is it means that right down here, this point, so let's see, this curve is f of x. We don't care what it is. And right here, this point right here, I'm going to color it in green. We have the point x comma f of x. We don't know what f of x is. It's just whatever y is when x is x. And over here, We started at x and we went over h. So I don't know exactly what this number is. But whatever this number is that's right down here, it's going to be x plus h. And f of x, this y value, is just going to be f of x plus h. Basically, whatever this number is, we plug it in here. Whatever we get out, that's right there. So by setting it up that way, they were able to do the following. They could say, okay, slope is change in y over change in x. And the way that we find that is by subtracting. So whatever this is, this change in y, to get from here to here, we just start with a higher number that we have, f of x plus h. We're going to subtract the smaller y value that we have, f of x. And for change in x, we're going to do the same thing. This is the larger x value, it's x plus h. And we're going to subtract the smaller x value, which is just x, to get the distance between the two. So here, this is literally rise over run. It's basically just a formula for slope. Notice x minus x is 0, so this is also written as f of x plus h minus f of x over h. If we find the limit as h approaches 0 of this, that means the 2 points get closer and closer until at the limit there's only 1 point and the line tangent to it. So what's going on is basically just that this h is shrinking. And as this h shrinks, it means that this dot is moving closer and closer and closer to that dot, or if you want to go the other way, this dot is moving closer and closer and closer to that dot, either way. And ultimately, it is that tangent line. That's what we were trying to find. So this is where the derivative rules come from. I'm going to give you a quick example here. So this is where the derivative rules come from. Let's say we have f of x equals x squared. We know our rule. F prime of x, we just bring down the exponent. Right like that. Here's the origin. We started off with the limit as h approaches 0 of f of x plus h minus f of x all over h. And because we've got this 0 right here, and we put 0 in here, we just said f of x minus f of x, we get 0 over 0, and so we have to massage it and cancel something out before we can find the limit. So f of x is x squared, so we're going to do x plus h squared minus x squared. And we can expand this out. X squared minus x squared is just 0. Now we can factor out an h. Cancel those out. Phew! Now we don't have any division by 0. We can just stick that 0 right in. Right like that. Same thing we had up there, except it took way longer. Now, basically what mathematicians did was they just did a whole bunch of these limit problems until they found out that there was a pattern, and that pattern was just to bring the exponent down and then subtract 1 from the exponent. And there's a reason for it. It's coming out of the binomial formula. This part right here, notice how when we expand it we have 2xh's, and that's where our 2x is coming from. Everything else ultimately goes away. But it is a very nice thing that we have these derivative rules, because that was really the beauty and the genius of calculus, was that rather than some poor sucker having to go through this procedure every single time, we could just apply those rules up there. So, our goal is that when we see something that's in this form, in this limit form, that we'll be able to recognize the special forms of the limits, write them as derivatives, and then work with them more easily. There are two forms that we'll see derivatives written as limits in. Just going to call them form 1 and form 2. And they both have the same basic idea. So it's still that we have some curve, and we still have 2 points that we're working with. But they're labeled slightly differently simply because one form is more useful for some things and one form is more useful for the other. This is the one that we just worked with. So in this is x. This is h. And so here we have, this is still f of x. Here we have x comma f of x. And this point is x plus h comma f of x plus h. Okay, so that gave us our form, a limit as h approaches 0, f of x plus h minus f of x all over h. And over here, we still have that line. We still have x. But now rather than having this be h, such as some distance over, this just has its own name, c. So we still have this rise over run. But this point right here, this is x comma f of x. And this point here is c comma f of c. It's 2 different variables. And so when we're finding this, we've got the limit, not as, there's no h, this distance isn't labeled like it was before, but simply as x approaches c, as x gets, and this dot moves closer and closer to that one. And the y value, the top y value, is just f of c, and the bottom value is f of x, and we've got the letters c and x. And when we have 2 points, we're trying to find the slope between them. We can write them in either order as long as we're consistent. We can either do f of x minus f of c over x minus c, or we could go the other way, f of c minus f of x, c minus x. The convention is that we're going to do the variables first. It would work out if we wrote it the other way, but this is the form that we're going to recognize. So let's do a little compare and contrast on these. On this one, the x-coordinate of the point we want the tangent line to goes in for x. On this one, the x-coordinate of the point we want the tangent line to goes in for C. So the types of problems that we're going to see is we're going to see that we want to find f of x and the x value at which we're taking the derivative. So on one hand, we're going to see this. We're going to see the limit as h approaches 0. 3 plus h squared minus 3 squared over h. And on this other side, we're going to see the limit as x approaches 3 of x squared minus 3 squared over x minus 3. On this side, the number with the plus h is the x value we take the derivative at. On this side, the value x approaches is the x value we take the derivative at. Whatever is being done to the number plus h is the function f of x. This is also going to be done to the number without h. Notice that this is 3 plus h squared, this is 3 squared. That means our function is x squared. Over here, whatever is done to the x in the numerator is the function f of x. So both of these mean they're saying that we're finding the derivative when x is 3, and the function that we have is whatever it is squared. So 3 plus h squared over here, x squared over here. So we would interpret it these both mean find the derivative of f of x equals x squared when x equals 3. We could do that easily enough. Take the derivative, f prime of x equals 2x, plug in 3, and we're good to go. So let's do a few examples. Rewrite each limit as the derivative of function at a number if possible. So let's start with the limit as h approaches 0. Square root of 4 plus h minus square root of 4 over h. So notice as we were looking back at our list, that's this pattern. We're seeing the h approaches 0. So whatever number is next to the h, that's 4. Whatever is being done to the 4 plus h, that's our function. So this means find the derivative of f of x equals the square root of x at x equals 4. That's all we're doing. So for the next one, that's this form, whatever's being done to the x, that's our function. The number right here is the number. So it's just e to the x, e to the number, it's the same thing. Find the derivative of f of x equals e to the x at x equals 5. How about the limit as h approaches 0 of e to the 4 plus h minus e to the 4th over h. Notice this is the h form again. So whatever's being done to the number plus h, so 4 plus h, that's sort of our x, so it's e to the x. And the number here next to the h is 4. So it's at x equals 4. Let's do this one. Limit as x approaches 0. F of x minus f of 0 over x. Now, this doesn't immediately look like one of these. We've got 0 over here, but that's h. We've got x over here, but that's a number, not 0. And also that we ought to have x minus some number in the denominator over here. But if we look at this, if we think of this as x approaching 0, then what's really down here is it's really minus 0. It's just that 0 would generally be invisible, not written. But once we put it in that form, it looks an awful lot like this. In fact, it looks almost identical to our original one. What we're doing is we're finding the derivative of f of x. We don't know what it is, but just f of x at x equals 0. Now let's try a fifth one. So let's do the limit as x approaches 0 of e to the x minus e to the 0. Now, our first thing do would be to say, okay, this is going to be e to the x, and it's going to be when x equals 0. But watch out. Both of these have something in the denominator. That rise over that run. This right here, this is not anything. It's not the special form. We can't do it. This one, to find the limit, we would just plug 0 in for x, e to the 0 minus e to the 0, plain old 0. Wouldn't have to do anything special. Similarly, we don't have a number down here. In order for it to match this form, we have to have x minus some number in the denominator. Notice that up here it was okay if we didn't, because it was really 0, and the 0 was really there, it was just invisible. But with this one we can't. We don't have that special form. If this was x minus 5, it'd be fine. If it was h to the 0 and there was sort of an x plus, or a number plus h in here, like 5 plus h to the 5th minus 5 to the 5th, then we could do it, but not with this form as written. For our final problem, let's look at something that's even a little bit different. Let's say that we know something about f of x. That is this curve right here. And what we want to know is the following true? The limit as x approaches 0 of f of x minus f of 0 over x equals 0. So the first thing we have to do is we have to translate this. Notice that when we've got this 0 here, we really just have an invisible 0 here if we want. So this is that second special form that we had. This is really saying the derivative of f of x at x equals 0 is 0. Is that true or not? Well, if we look over here, derivative, that's the slope of the tangent line. Slope of the tangent line at x equals 0, sure indeed looks like 0. So we would say that this is indeed true. It is true because the slope of the tangent line to f of x at x equals 0 is in fact 0.